All right, let's try this circuit. We have a circuit again with a switch that opens at t is equal to 0. We have an independent current source, two resistors, and an inductor in our passive network. So what we're asked to find is the current through this resistor. This has a small r, I think we mean a capital R. And we want to find that current at just before the switch is opened, just after the switch is opened, a very long time after the switch is opened, and at 15 milliseconds after the switch is opened. So again, since there's a switch in here, we have two circuits. At t less than 0, we just have this 10 amp source flowing through. Right, at t less than 0, this is shorted, so the 10 amps is going to flow this way, and we're going to get zero current that way. So we really have a passive network that's not connected to anything until this switch opens. So once this switch opens, we'll analyze at t is equal to 0 plus. So we know at 0 minus, our IR of 0 minus was equal to 0 amps. We also have that our IL of 0 minus was equal to 0 amps. And that's key because that's what can't change at the discontinuity. So that's also equal to our IL of 0 plus. So that's the key when we go to analyze this. So we'll just analyze it at 0 plus. And so at t greater than 0, that's when we can find our time constant. So our time constant, again, is from the perspective of the inductor. So if we're looking in from the inductor here, we have to find our equivalent resistance, right? So let's find this first. Our tau is equal to our LEQ over REQ. And in this case, our LEQ is just equal to our 0.1 Henry. We only have one inductor in the network. And what does this resistor see? Well, it sees 60 ohms on this side and 40 ohms on this side. When we go, does it see over here where we got to kill the current source? When we kill the current source, we open it. So this is all open from the perspective of the inductor, what it sees. So it just sees the 40 ohms plus the 60 ohms in series. So 40 plus 60, they're in series. So that's divided by 100. So that's equal to 10 to the negative 3 seconds, or 1 millisecond. So if we want to find the current at 15 milliseconds, well, that's 15 times. So that's going to be a very long time away. So let's instead just find our current at 1.5 milliseconds to make it a little bit more interesting. So there's our time constant. That doesn't help us find IR of 0 plus. What helps us find IR of 0 plus, now we just need to consider the instant of time when this inductor has flowing through it. It still has just flowing through it. Our IL of 0 plus is equal to 0 amps. So our IR of 0 plus, if we do a KCL up here at node A, that's flowing out. It's equal to 10 milliamps flowing in minus our IL of 0 plus flowing out. Well, that's equal to 0. So this is just equal to, since that's 0, well, we shouldn't just cross it out like that. It just happens to be equal to 0, IL of 0 plus. So we'll write this out. 10 milliamps minus 0 milliamps, or that's equal to our 10 milliamps. So we'll write that up here, 10 milliamps. Our IR of infinity, again, we can find that as a DC circuit. At DC, what we have is that the voltage across the inductor is equal to 0. So what we have is our VL of infinity is equal to 0. It looks like a short circuit because VL is L di dt. Nothing's changing with time any longer. So as t approaches infinity here, how are we going to find this current through the resistor? Well, the current through the resistor, it's just going to be equal to this VR. We'll call it VR1. So we can say our VR1 is equal to VL plus, and we'll call this VR2 plus VR2. So it's just equal to, since that's equal to 0, our VR1 is going to equal our VR2, is going to equal VR2. When resistors have the same voltage across them, then we can use our current division, right? So by current division, oops, I don't know, current division, we can say that our IR is equal to that 10 milliamps times, we'll just do, it's 1 over 60 divided by 1 over 60 plus 1 over 40. And that's just going to be equal to our, that's going to give us 4/10 or 4 milliamps. So we got our 4 milliamps here. And now if we want to find our IR of t then is equal to our IF plus IN, or equal to our IR of infinity plus some A e to the negative t over tau, which is 1 millisecond. We don't need to know that's 1 millisecond to evaluate it at t is equal to infinity, but so it's equal to our 4 milliamp plus A e to the negative t over tau. We find A with our initial conditions. We've got to make sure we use 0 plus. So our 0 plus now is for the current through the to that resistor is equal to 10 milliamps. So we have our 4 milliamp plus A e to the 0, which equals 10 milliamp. So our A is equal to 10 milliamp minus 4 milliamp, or equals 6 milliamp, and we get that our IR of t is equal to 4 milliamp plus 6 milliamp e to the negative t over 1, what is it? 1 millisecond? Is it 1 millisecond? 1 millisecond. And that's at t greater than 0, not greater than or equal to 0. So that's our IR of t that we found. We're asked to find IR. We changed it to 1.5 milliseconds. So our IR, we'll go down here, our IR of 1.5 milliseconds, that's equal to 4 milliamp plus 6 milliamp times e to the negative 1.5 over 1, or 1.5 milliseconds over 1 millisecond. So that's going to be equal to 4 plus 6 e to the negative 1.5 milliamp. And you can plug this in to check it, but that's equal to about 5.339 milliamp. So we'll write that in up here. 5.339 milliamp. So we're at 10. We're heading down to 4 within 1.5 time constants. We're all the way down to 5.339 milliamps. So we should always graph that. So let's just graph that here on the next page. We have our current. We'll do our time. We'll do our time in milliseconds, and we have our IR at t less than 0. Gotta go back and check what it was. I forgot. T less than 0. Well, it was 0. It was 0, jumped up to 10. So we had 0, jumped up to 10, and then it came down as time approached infinity. It was, I forgot already. I think it was 4. So it was 4. So we're at 10 here. So there's our 10. If that's 10, let's say this is 4, and that's what it's going to go down to. So our IR is in milliamps, and if this is one time constant, that's our time constant is is just 1 millisecond. 1, 2, 3, 4, 5. By 5, we're all the way down. By one time constant, here's our we're whatever 63% of the way down, or we have 37% left. So we're coming down like this. All right, so that's this example.